Hi, this is Maggie. In this video we're going to discuss projectile motion. This is a program built from our template in which a robot falls from the top of the screen to the bottom. When something falls, gravity acts to increase its velocity over time or accelerate the object. The full equation for this motion in the y direction is y equals the initial y location plus the initial y velocity times the amount of time the object has been falling minus 1/2 the acceleration due to gravity times the amount of time the object has been falling squared. With the falling robot, the original velocity, because it is falling and not jumping, is 0. So we need only the negative 1/2 gravity time squared. In our program, this is actually plus 1/2 gravity time squared because of the inverted y-axis, because y increases as we move down rather than as we move up. So we're adding 1/2 multiplied by a gravity constant multiplied by time squared. In our program, time is a counter that increases as the robot falls. Time is measured in seconds, and we increase it by 1/30th each time through the game loop, so time is pretty close to real time. Our gravity constant is calculated based on the scale of our image so that it approximates Earth's gravity of 9.8 meters per second squared. If we are going to simulate a projectile that isn't falling, in other words, something that is thrown or catapulted or otherwise acted on by some kind of force to send it into the air, then we'll use the full equation to calculate the x and y components of our object's location. Let's look at how this is done using listing 9.6 from your text. I'll start by demonstrating what the program does. When it opens, I can see a ball at the bottom left corner of the screen, and the caption of the window is angle 0, speed 100. I can use the up and down arrows to change the angle in increments of 10. So let me increase that to 50. And I can use the left and right arrows to change the speed. So let me increase that to 150. And then when I press the space bar, I watch the projectile fly through the air tracing a parabola. A flag is placed by the program where the ball lands, and the ball is replaced to the bottom left corner of the screen. Let's see how this is done. In the event loop, you can see that the arrow key presses are processed by adding or subtracting 10 from the angle and speed variables. There are also constraints so that neither is ever set below 0 and angle is never set above 90 degrees. If the user presses the space bar, a Boolean flag shoot is set to true. Below the event loop within the game loop, there is a block of code that calculates the new location of the projectile if shoot is true. After that block, the caption is set to the current values of angle and speed, and the background and projectile are blitted to the screen, which is then flipped to show the user the new location of the ball, if any. Our focus will be on this block of code that calculates the x and y location of the ball if it has been shot. So first, time is incremented. Here the motion is sped up. Instead of adding 1/30th as we did in our falling program, we add 1/15th each time through the loop. Then the location is calculated. Let's start with the x equation, which is first. Recall the equation from the text. X equals the initial x location plus the initial x velocity times time. Well, we know what time is. It's a variable we start incrementing when the user presses the spacebar, which corresponds with the launching of the ball. It will increase as time passes, and it represents seconds. And the initial x position is 0 because we're at the left side of the screen. But we could start anywhere on the screen and we just plug that location in here. That is where the ball starts moving from in the x direction. But then there is the initial velocity of x. What is that? Our velocity in this program is represented in polar coordinates, angle, and speed. Recall that we can visualize this as a vector, and we can visualize the vector as a right triangle that is composed of an x component and a y component. Those are the x and y components of the initial velocity of our projectile. It is the velocity we give the ball, and the x velocity will never change because a body in motion remains in motion unless acted on by another force. In this simulation, there are no forces in the x direction. So we can calculate our initial x velocity as the speed multiplied by the cosine of the angle. Let's look at that in the code. We have a variable called start x, which is holding that starting location of x, which is 0 in our game. Just for fun, let's change that, and you can see the program works exactly the same, except the ball begins in a new place. I'll set it to 100, and we'll run the program. And there's the ball. It's moved out from the wall a bit, and I'll increase the angle. Press space. The ball traces a parabola, lands, and then returns to its new original location. A flag marks where it landed. Okay, so that's the starting point in the x coordinate for our ball stored in start x. And then the next term is initial velocity of x times time. The initial velocity is cos angle, and we need to convert that angle to radians because our angle is expressed in degrees. So math.cos, open paren, math.radians, open paren, angle, close paren, times speed. And then that is multiplied by time. That gives us the new x coordinate for the ball. Now, the y coordinate is a longer equation because gravity is involved, but it's no more difficult. We have start y, just as we have start x, and start y is the bottom of the screen. And then we subtract from that, because of our inverted coordinate system, the sine of the angle times speed, which is the initial velocity in the y direction, and multiply that by time. So far it's just like the x equation. And then we add to that 1/2 times gravity times time squared, just like in our falling program. In this program, gravity is 72 because that is the value that was calculated based on the scale and the value that seems to make the program appear realistic. Now, the program does also check to see if the projectile has reached the ground, and if it has, it resets everything. The x and y to the starting, x and y, shoot to false, and time to 0, and it puts a flag at the location where the ball landed. So that's projectile motion, and as in that introductory physics class you may have taken, it's very simplified. No air resistance or wind or anything else like spin of the ball that might complicate the equation. But it's good enough to give a realistic looking projectile, and it's very useful in many, many gaming situations. I recommend you try recreating this program and then make some modifications. For example, you might find a little cannon image and shoot the ball out of the cannon. You could try shooting the ball from a moving cannon. Make changes that will challenge you to understand and modify the code that implements the projectile motion equations. When you can work with these successfully in a few different situations, you're ready to move on.